Well,
Yes.
I think it's time to introduce our speaker. Let's say a few words about Dr. Muhammad Norhaffis Mustafa. Norhaffis Mustafa initiated his academic odyssey at University Putra, Malaysia, culminating in the acquisition of a bachelor degrees in chemistry, a four-year endeavor spanning from 2011 to 2014. Subsequently, he pursued further academic advancement, culminating in a master's degree in material science, attained over a 3 year period from 2015 to 2017. His academic trajectory culminated with a successful completion of a doctoral philosophy degree in material science, an accomplishment realized within a 2 year time frame spanning from 2018 to 2020. Currently, he serves as a research fellow at Sunway University, focusing on developing innovative materials for smart windows that respond to electricity, light, or temperature change. His notable achievements include over 25 research publications, 4 patents, and awards such as the Metron Young Chemistry Award and Anujera Sisuwa Semerla Master Science in 2018. After Dr. Mohammad's presentation, there will be an opportunity for questions. You can submit your questions in the chat on this session, and we will share them with Dr. Mohammad at the final of his lecture. Well, I think it's time. Let's get started. Professor Mohammad,
Okay,
go ahead.
so let me share my screen. First of all, can you hear me?
Yeah, everything is right.
Okay, so hi, a very good day. So today I'm going to, first of all, I would like to acknowledge the committee for inviting me for the student chapter to present on RSM, response surface methodology, which is one of the optimization tool, which RSM is a powerful tool for optimizing material. It is not just material, also to optimize the procedure, the methods in energy storage and harvesting, although in other applications also. So my name is Dr. Muhammad Norhaffis. I'm from Sunway University under the Center of Electrochemical Energy and Sustainable Technology. So a little bit bibliography, I don't need to explain a little bit because the moderator already explained a lot of them. So basically my research interest, because my master and PhD on the solar cell, I did the dye-sensitized solar cell. And during my postdoctoral, I did a supercapacitor, dual application supercapacitor like electrochromic supercapacitor, little bit on supercapacitor and rechargeable battery, and also last but not least on thermoelectric. So this is the outline for today's presentation. So we don't have much. We have 5 major outline. The first one is introduction to optimization, why we need to do the optimization. Second one on the overview for RSM, what is response surface methodology. And we are going to do the experimental design in RSM and do some case study and step by step how you're going to master the software in terms of design of expert, in terms of running the RSM in the software. And last but not least, interpreting the RSM results and making the decision whether the model is good, valid, or not. Okay, without further ado, let's jump to the first subtopic, introduction to optimization. When we talk about optimization, a lot of people already know about the definition. So what is the important application and also challenges? So optimization is the process of making something effective. So we don't want to do an experiment without direct goals or objective. So by optimizing something, we want to make it effective, efficient, and functional as possible. Involve adjusting our variables. We have a lot of parameter factor that affecting our experimental, that affecting our response. So what we're going to do with that parameter. So it is a system to maximize or minimize a desired outcome. when we talk about response surface methodology, we want to optimize our surface response to be maximized or minimized. So later you know what to be maximized and what to be minimized. So basically, it involves three major things: variables, your factor, your constraint. Of course, we have limitation in optimization, and also the objective to maximize or minimize. And important for optimization, first, we want to reduce the cost. We want to have a high efficient as possible. And to improve the performance, of course, for sustainability, we don't want to waste our material, and also for quality control. Before we talk about the validity, repeatability, reproducibility, that's why we do the optimization. And the application, either you can synthesize new material, you can optimize new material, or the fabrication process. For example, if you are using hydrothermal, you can actually optimize the temperature, the time, and so on. However, you also can optimize both simultaneously. But in traditional optimization, it's quite hard because you need to have a lot of constraint or limitation in order to do it traditionally. So some of the challenges, which are the first one, is the complexity of the system. If you have one or two parameter, it's okay to do the traditional optimization. But how come if you want to study 3, 4, and 5 parameters simultaneously? At the same time, you want to see the interaction between variables. So one of the challenges is complexity of system will be very big and very difficult. Second is about time and resource. You don't want to do a lot of experiment because limitation in your time and also your resource. And last but not least, finding the absolute best solution might be hard because you don't have a very systematic approach. Then we jump into response surface methodology. Why it's important to be used as optimization tool. We're going to see a little bit on definition, the importance here, and also the key component that you might learn before you dive into depth of the response surface methodology. So talking about RSM is a statistical and mathematical approach. It's already designed for you. If you didn't know about the coding, don't know about the machine learning, Python, and so on, it's already designed for you. You just put input, follow step by step how to put your parameter, your variable, what is your surface response, then they will design for you the set of experiment. So again, RSM is statistical and mathematical approach for optimizing process with multiple variables. The minimum is 2, maximum can be up to 20, 40, and so on. The purpose for RSM is used to understand and model the relationship between input parameter, input factor, or we call that independent parameter, and the output response, which is your surface response. In the end, the target is to find the optimal condition. Then by fitting a response surface to the experimental data, there will be a lot of graph for you to see and to analyze. So RSM have visualize what happened during the optimization of material, optimization of the procedure, and predict how changing one factor can affect the outcome. We want to see the significance of individual factor and significance of joint factor towards the surface response. So why we use RSM? Why don't we just stick to the traditional optimization? So first, systematic approach. RSM provides a structured approach for adjusting multiple factors simultaneously. The important thing here, simultaneously, and to find the best outcome efficiency. Second thing is we want to understand the factor interaction. So we want to understand factor A and factor B. What is their interaction toward the surface response, and simultaneously changing both factor, what happened to our surface response. Is it good or is it bad? Is it make the model more accurate or not? The third thing is to reduce the experimental run. Without a very good target or objective, you don't know how to start your optimization. So by RSM, they will suggest you, they will design for you set of experiment. You just follow the set of experiment, then you can get the optimized procedure or optimized material. Last but not least, identify the optimal condition. in the end, when we optimize something, we want to find the optimum recipe. So that's why we should use the RSM. So the model and response surface help identify the global optimum even in the complex system. Even if you have 3, 4 variables that you want to see the interaction simultaneously, it will help you how to see the best optimum condition for that purposes. So let's go to some key component in RSM. So what are the key component that you need to know first before you're going to use RSM? First of all is response. So we need to know our response. Let's say in energy storage application, if you're dealing with supercapacitor, your response is specific capacitance. If you are dealing with the rechargeable battery, you are dealing with specific capacity. So you need to know your response, which is the outcome that we are trying to maximize or minimize. So in terms of like energy storage, supercapacitor and also lithium-ion battery, we also want to see the retention, stability retention. That also can be your response. Like in sensor, you're going to minimize your response. Like you want to have a very low limit of detection. That also can be your response. So understanding your response is very important. Second thing is about the factor. Before you are dealing with factor, you need to know you want to optimize the material or you want to optimize the procedure. Which one? Or if you already expert in this software, you can optimize both simultaneously. But the number of factors will be higher compared to optimize them individually. So factors are variables that influence the response. Let's say you're going to use what microwave, need to have temperature and the reaction time. And also if you want to see the material, concentration of each precursor is important. You need to know the ratio of each concentration of your material. So the factor, how you determine and how you select the factor is very important. That's why you need to understand your material and also you need to understand your procedure before selecting the factor. And then the third key point of RSM is level. Level is also important because different value is assigned to each factor. Let's say you have one of the factor is temperature. So that temperature can go for negative, your machine can go to negative and can go to very high at high temperature like 200, 1000 and so on. So how you going to limit your temperature? So it's very important to set the range of your parameter, this range of your level, the level of your factor. So you cannot go like 0 degree to 1000 degree because some reaction doesn't occur at very large range. For example, your reaction occur from 100 to 200 degrees Celsius. So you need to do some preliminary experiment to determine the correct range. Then say we have take some analogy. If you want to measure the length of the hair, you just use normal ruler. If you want to measure the length of the road, so you don't need to use a small ruler, cannot. You need to use a measuring tape and so on. So the tool of measuring your factor is important. If you select different range, means that it's impossible for model in the RSM to fit your model. Last but not least is response surface. Because in RSM, in the end, they will give you a graph, a 3D and 2D graph. So before you are dealing with RSM, you must anticipate something. What anticipation that you have in the graph? If you expect a strong curvature, means that a very strong interaction means your model, you need to predict a quadratic model. If you just thinking when you increase your parameter, what happen is your parameter will increase exponentially, will increase linearly, then your model will be linear. So depending on what you're expecting, it's very easy to optimize the model. If you expect a curvature, then go for quadratic or cubic. If you expect a linear, then just choose a linear model. So you need to see from the paper and journal what are you expecting on the response surface. Okay, enough with that. Then go to the experimental design. Because these designs as per software, they have a lot of designs in the software. They already designed for you. You just choose them based on the ability of your material or procedure to adapt to the design. Okay, we have four main designs, and the common one is central composite design, CCD, and box backend design, BBD. This is the most common and most widely used design in RSM. We also have full factorial design and dollar design. So CCD is the most popular design in RSM, used to fit a second order, which is the quadratic model, especially useful when you expect a strong curvature in your response. So, however, CCD is not all very good, because one of the weakness of central composite design, when you put your level of your parameter, they tend to go to the very critical value and very low value and very high value. So it's very difficult for central composite design. Let's say your optimum temperature is around 40 degrees Celsius. So for central composite design, they tend to go like 0 degree, 10 degree, very low temperature and very high, for example, 100 and so on. So you need to choose your design based on what your model, what your material capable to achieve. Okay, so next is box backend. Box backend is second best model compared to central composite design. The best thing about box backend, the point is separate around the box. So if your material or your procedure cannot go to extreme corner point, so if sometimes may be impractical or unsafe for your material, it might be degrade at high temperature, or it might not responding in low temperature. So it suggests you to use the box backend. And one of the benefits for box backend, the number of experiments is slightly reduced compared to central composite design. And we also have full factorial. This happens when you have unlimited time and unlimited resources. You can do the full factorial design. The full factorial design tests every possible combination of factors at all levels. While this is very true, it can become inefficient with a large number of factors or levels due to the number of required experiments, because the number of experiments is very overwhelmed in this case. Okay, then you might heard of dollar design, but I never done with the dollar design. It's less common, but highly efficient for exploring multifunctional response surface. Use fewer experiment point and CCD and box backend. And in this case, you can have fewer number of runs for dollar design. So which one to use? Which one you want to use? So you can see from this table, you can choose and decide which is suitable for your experiment. If you expect a very significant curvature, go for central composite design. If you want a balanced design without go to the extreme value, go to the box backend. If you have time, have a lot of resources, you can go for full factorial design. And if you want to reduce number of experiments, you can go for dollar design. Okay, you can see the advantages and also disadvantages. So let's go to the case study and software demo. In this slide onwards, so I'm going to show you step-by-step procedure, how when you have the software, how you're going to input your parameter and surface response, import and important data analysis to show whether it's a good result or not. And if you have a bad result, so how you're going to overcome that case. Okay, let's start with the software. Okay, this is the design expert software. Now I think it's already version 13, so I'm showing you the version 12. So it's almost the interface is the same. It's no big deal. So you can, if you are newbie, you can click Designs Wizard. They will teach you one by one if you don't know anything. So if you already have a little bit knowledge by attending this short webinar, you can just click with the new design. They will show you, I will show you one by one how to do it. And if you already have a design, you can click the open design. So first click the new design. Then this interface will come up when you click the new designs. You have randomized, regular 2 level, and so on. You need to choose the response surface here. So click the response surface, then this interface will pop up. From here, I choose the central composite because I'm going to teach you how to do the central composite. You can also choose the box beacon here, box beacon and also optimal, which one is preferable for you. At the left here, you can see we have central composites, box beacon, and optimal, and other designs here. So first, the numeric factor is the number of factors that you're going to put in your software. The minimum is 2, and the maximum can be to 50 per factor. So you can put how much you want. So my suggestion for the first time, you better choose 2 or 3 factors. If you're already expert, you can go to 4 or 5 factors, because they increase the number of factors, the set of experiment designed by the software also will be increased also. Okay, so just put the name of your factor. Let's say I have choose 3 factors, and my parameter is time, temperature, because I'm using a microwave synthesis. Important thing is about the temperature and also the deposition time. And I'm going to mix with the concentration of my precursor, because I know that the precursor concentration also affect the process. So I put the units, and low and high means that what is your range of factor. For example, time, my range of factor 10 seconds to 30 seconds. So I expected at this interval, the deposition will happen. That's for example. And temperature, because you can know by doing the preliminary experiment, or you can read some journal and make a data, see the data. Majority at the journal, they deposit at what temperature? So you can see the data and you can choose the low and also the high temperature that the experiment will work out for you. Okay, then also you see about the concentration. One of the way is you can abstract the information from the literature review or from the journal. One of the way, if you are that curious, if you don't want to believe the journal, you are that curious, you think, I'm not sure about the temperature, I'm going to test myself. So what you need to do, we just fix the time and the concentration and try the lowest temperature and also the highest temperature, and see whether the trend is what you desire. If let's say, when you try 80 and 120, you can see that at 80 degrees, let's see about supercapacitor, the performance is around 100 farad per gram. When you go to 120, you got the performance around 200 farad per gram. So you might be curious what happened at 150, 200. You can also try at that temperature and to see if the trend already falling down, no need to go beyond the 120 degrees Celsius. That's how you determine the level of your factor. So you need to try at low temperature and also at high temperature. The same goes for the time and also concentration. There are some preliminary experiments that you need to do before determining the set or the level of the factor. So it's very important, because if you just do the experiment without the preliminary or without extracting data from the journal or literature review, if you just put the number, then you will be headache when you facing the data or the result in the software later on. Okay, next, you click option here. When you click option, you can choose here the centered point. Centered point, by default, the model will give the centered point to 6 centered points. The minimum you can put 3 centered points. You can reduce the number of center points here and choose the 5th centered. Because if your model has the capability to go to the decimal and negative point, you can go to rotatable and other. But if you want to have something with the whole number, you can go to the 5th centered. Just click 5th centered. Then click OK. Then the next interface after you click OK, we go to the central composite design, putting your response. So let's say you are doing supercapacitor. So your response is specific capacitance. The unit is farad per gram. If you are using a rechargeable battery like lithium-ion battery, sodium-ion battery, you can put here specific capacity or retention study, like the unit is milliampere hour per gram. So make sure to put the unit correctly later on, because the unit will reflect in the graph. If you just do the acronym, then everything in the graph will do the acronym. Okay, so after you click finish here, after you click finish, what happened? So you will have this interface. They will show you the design aspect. Software will show you the designs of your experiment. So based on these 3 parameters, you have 17 experiments to be done. And let's say the time you make a mistake, the time is not in seconds, in minutes. What you need to do, you just right click and change to minute. Okay, that's also can. So then they will change accordingly. So in this set of experiment, you can see that it's not 17 independent, unique experiments. Some of them are repetitive. If you remember before, you have the repeat point at the middle, which is 3 repeatable points. You can see here your repeat point is around, you can see 20, 100. You got 1 here, 1 here, and 1 here. Okay, this is the repeat point. So total, the number of experiments is actually 14 experiments, 15 experiments with 3 repeated values. So that's the number of experiments you need to done. So after that, you do the experiment one by one. You prepare the time, temperature, and the precursor at the desired molarity and desired temperature and desired time. Then you record your response, which is specific capacity, specific capacity. You can, in supercapacitor, you can either using the cyclic voltammetry, or you can use the galvanostatic charge discharge. Same goes for lithium-ion battery, sodium-ion battery. You can choose the charge discharge to calculate the specific capacity. If you are in sensor field, you can calculate the limit of detection by DPV or CV, and a lot of things depends on your response, depends on your application. So after that, and after you finish, you can click here, the analysis, which is R1, specific capacitance. So you can click the specific capacitance. So after you click the specific capacitance, this interface will pop up. In this interface, so start with transform. Transform, you can use the transform when you expect transformation is needed in your model. Some need the model to have reduced square root, natural base, and so on. This is later if your model is not fitted, and to fit the model, you need to transform the model. Why? So far, if they give you a hint here, a ratio greater than 10 usually indicates a transformation is needed. If you see your ratio is only 3 point something, no need to do the transformation. Okay, then we go to the second interface, which is fit summary. So at the second interface, they will show you a little bit summary, which model is good, which model is not good. So the bold one is the suggested model. Meanwhile, the design thinks that this model fits very well to your case study. So how to know? In the blink of eye, so to know it, just look at the p-value. If the p-value less than 0.001, and also your adjusted R square and R square close to 1, means that the model fits very well. Normally, they will bold the fitted model. And they will also give you the alias model. But the alias model is the second best model in your design. So next, what you need to do, see the second thing. Second thing here is about the sum of square, the F value, and P value. The same thing. The best model in this case is the quadratic. Okay, next, click the third interface, which is FX model. So in this model, automatically they will choose quadratic because quadratic is your best model. If you don't want quadratic, you want to change, you can click here. You can change to cubic and so on. But I encourage you to choose the one that suggested by the model. So the next interface is the ANOVA. In the ANOVA, there are some important things that you need to highlight. And before that, maybe some of you are new to this optimization. So let me share with you some of the terms that you need to know. So first of all, is sum of square. So sum of square measure the variation in the data. So you can see you have a lot of sum of square. For example, sum of square of your model, which is the total sum of square. You can get the value of 3.461 exponent 10 to the power of 5 by adding all the sum of square of model set term. A, B, C, A, B, A, C, B, C, A square, B square, and C square. If you add all, you can get the total sum of square of your model. Next is degree of freedom. So degree of freedom is a quantity, quantify the number of independent pieces of information that your model or model term holds. Let's say the model have degree of freedom 9, means that you have 9 subset of your model term. Let's say you have model term A, B, C, AB, AC, DC, A square, B square, and C square. So you have 9 subset model. That's why the degree of freedom is 9. And the rest is 1 because all is subset model term. And for your residual, your degree of freedom is 7 because you have 2 insignificant model term. Later, we show you how the model term can be insignificant. So in this case, the model term is insignificant because the p-value is more than 0.05. Here, 0.61 and 5.2. AC and BC is insignificant model term because the p-value is more than 0.05. Okay, that's why the residual degree of freedom is 7. So your pure error depends on how many insignificant model term you have 2. Lack of fit, the degree of freedom is 5 because 7 minus 2 is 5. Okay, that's about degree of freedom. Then you need to know about the term mean square. So what is mean square? So mean square is variance estimate. So you can get the value of mean square by dividing the sum of square of the regression divide your degree of freedom. If you don't believe, click your calculator. For example, 3.461 exponent 10 power 5 divided by 9, you can get the mean square value. Then you can have the f square, f value, and also p value. So f value, the meaning of f value is the model explain more variance than random error. We expecting the f value to be big. So because we want the model to explain more variance than random error. So the f value also, the bigger f value also signifies a small p-value. So in terms of p-value, the model shows that the p-value should be less than 0.05. Means that you're only expecting 5%. The result is due to the noise, due to the error. In another word, p-value less than 0.05, saying that your model predictability has 95% confidence level, saying that your model is very good. So that's how you determine the p-value. But depend on the application, some application that involve humans producing a new drug, the p-value might be different. So the p-value might be a little bit lower, like 0.01. You want to have 99% accuracy. Or even 0.001, you want to have 99.99% accuracy. So you can determine your p-value. So the lower, the better. So in this case, by default, the model will set the p-value to be 0.05, means that if you have the value less than 0.05, your model term is significant. Significance means it's very well fitted. So in this case, your overall model is significant, and model term A, B, C, AB, A square, B square, and C square are significant. So you have 7 significant. So here, the residual is 7. You can see you have 7 significant model terms. So the next important thing about this interface is to see the lag of fit. The lag of fit should not significant. The lack of fit depends on your repeated value at the middle point. In your previous interface, you can see the repeated, we try to repeat 3 times. So for lack of fit, it should be not significant. The 3 repeated experiment, the value should close to each other. And the value should not vary to each other. That's why it should not be significant, the lack of fit. Okay, next interface is about your fit statistic. Okay, as general, for standard deviation, you want to have a small standard deviation. Standard deviation means that the spread of your data around the mean value. In this case, the mean value is 5 or 6. Means that all of 17 experiments when you're done, you expecting the value to be 506 farad per gram. And for your standard deviation, if small, means that the data is well fitted. If you have a very big standard deviation, means that your data spread very big around your expected value. So it's not very good. If you want a very high reproducibility and repeatability, standard deviation should be small. For R-square, adjusted R-square, and predicted R-square, we know that all the R-square we want to have as close to 1 as possible. For the R-square, to have a very good close to 1, explain the variability in the response variable. For adjusted and predicted, if your R-square close to 1, indicates that it's very good, well fitted. If the difference between adjusted R-square and predicted R-square more than 0.2, means that your model is overfitting. So we don't want our model to be overfitting, which is not very good. That's why we try to minimize the difference between adjusted R-square and predicted R-square to less than 0.2. So it's very important. And for added precision, we want to have a ratio more than 4, because it is a ratio of your signal to noise ratio. The bigger ratio is better for added precision. So that's how you're going to know whether your model is good or not in the ANOVA interface. So recap a little bit, you need to know about the significance of your model and model term, and the lack of it should not be significant, and also the R-square value should close to 1. That's the important thing in this interface. Then we can go to the diagnostic interface. The next interface is this diagnostic interface. For the diagnostic interface, before you go to that, you need to know about the coded factor and also actual factor. So by fitting your experiment into either quadratic, cubic, and so on, the model will generate a regression equation for you. So there are 2 equations. One is based on the coded factor. Coded factor means that you just substitute either +1 or -1 to the value of your parameter. However, for actual factor, you can substitute the real value with the real SI unit in your parameter, like in this case, time, temperature, and concentration of frequency. And when you substitute any value, you can get the desired specific capacitance, how much your model will anticipate to produce the specific capacitance. So you can also include this regression equation in your paper and so on. Okay, move to the diagnostic. In diagnostic, you can see you have a lot of graph. Normal plot, residual, we have good distance, box score, predicted, and everything. We're just going to discuss the important graph that you can discuss based on the results. The first one is the normal probability plot. Okay, this normal probability plot is normal probability versus the external standardized residual. So you need to see your data lies on the straight lines, indicating what? Indicating the error is normally distributed. We don't want, in some cases, if you wrongly determine your level, your set of experiment, the range of factors, you will notice a heavy head or heavy tail. So it depends on your ability to determine the correct range. You will get a very smooth data that lies on the straight line. indicating the error is normally distributed. Second thing is about the graph of predicted versus actual. We know that the model also have the prediction. If you do or input your experimental data, the model will show the predicted how large is vary with your data. What is the variance, the difference between the data and the experimental setup by the design. So if your design is very accurate, what you did in experimental reflect what is predicted by the model, your data relies on the straight line, indicates that what is predicted is almost the same with what actual doing in the lab. Okay, next you can go to the perturbation plot. Perturbation plot is important, and actually the explanation is quite lengthy. In short, what you need to know about perturbation, you can see the interaction between each independent parameter simultaneously toward the surface response. In this case, your y-axis is surface response specific capacitance. So you can see the curvature of your independent parameter. You can see at low coded factor, all is low, at certain point in the middle, the result is higher. And when you increase a little bit, the trend a little bit lower. So this is the trend that we expect a curvature interaction. That's why the model predicted quality is the best for you. If you just observe a very linear increase or linear decrease, then linear or two-factor integer will be stochastic by the model. So depend on the behavior of the data. So the type of model also different. If you don't like to use the perturbation, you can go to the one plot factor. In one plot factor, you can actually define what happened between each independent parameter towards your surface response. What happened when you increase the time, and what happened when you increase temperature and frequency toward your surface response. Okay, move on to the contour. So contour graph like this, you can see the interaction based on the shape of the contour. The different shape will give you different interaction. So you can see here, for example, in this table, if you have elliptical like this one, elliptical, so it signifies a very significant interaction between each independent parameter with your surface response. If your factor is very circular, this one is very circular, so means there is no significant interaction. Can also have a saddle, like a horse saddle, so means that one factor might be very significant, the rest might be not significant. It can be parabolic, linear, and irregular. So you can explain the 2D interaction based on the shape of your contour. And last but not least, you can get your 3D surface graph. So by having the 3D, actually, if you open the model, you can move around this 3D to get a very good curvature. The main point is to observe the curvature. How curvature your 3D model toward your surface response. The more intense the curvature means that that model term is very significant. You can see here, you have a B. Temperature is very significant. That's why it's very good, very intense, the curvature. Time also very significant. And factor A and B, you can choose here. You can change to BC and also CB. Depends on your number of model. So you can see the interaction between the two parameters towards the specific capacitance. Okay, so before we end our ANOVA, so they will ask you to do the validation test. Because ANOVA analysis itself is not that accurate because you didn't validate that yet. So validation test is important because in the end, what the model stochastic, you need to prove whether it's true or not. So you click here, under the optimization tab, you can go to numerical, double click on the numerical. There will open interface like this one. So all your parameter will pop up, all your response surface surface response will also pop out. So you need to set the goal in your mind. For example, the time your goal to be in range, temperature you want to be in range, and concentration also you want to be in range. If some of parameter you don't want to be in range, you want to set equal to what? For example, you want the time equal to 10 minutes. You don't want anything else. You want 10 minutes. You also can change here in the goal. And for specific capacitance in supercapacitor, normally we want to maximize it. If you have a sensor limit of detection, you want to minimize, you can just here minimize. If you don't care, you don't want maximize or minimize, you can put in the range. Okay, so just put it. And then what you need to do, click the solution tab. So you click the solution, there will have 100 solutions. So in my case, I choose one solution and I try to replicate 3 to 5 times. And I will calculate the residual standard error or percentage of error. So less than 5% indicates that the model can predict up to 95%. So it's good. If you want to choose either 1 to 3 solution, if you want to choose top 3 solution and do the repeatability and compare the value theoretical specific capacitance with the theoretic experimental value also can, it's no problem. So this is the residual standard error that you're going to do and calculate. And if you got the standard RSC less than 5% is good. This is the experimental on dye-sensitized solar cell, whereby my parameter is concentration of PBA, the polymer, and volume of TTIP, the source of titanium. And I calculate the power conversion efficiency and see the predicted and experimental value. I repeat 5 times and calculate the RSC to know whether the model have high confidence level or not. Okay, so before we see the error or the mistake that happened in RSM, let's see some recap in the RSM procedure. So by starting the experiment, you design your experiment, you fabricate, for example, this is a compact layer for DSSC, splitting the model and optimize the response. And if during the validation or verification of model, you get the RSC is very big, 10%, 20%. So what you need to do is you need to find the cause and do the corrective action. Instead, you need to study back the limits of the level of your parameter and go back and design back your experiment. Until you get the RSC less than 5%, then you can end your optimization. Instead, you can carry out to the other analyzation like electrochemical analyzation or physical analyzation. And before we stop, let's do some common problem in RSM. So a lot of people might wonder and they might facing some problem. Maybe the model is not significant. So see how the model is not significant. So this is the very first criteria. If the model is not significant, means that you can see here the first step is the model is not significant. Means that no point to look at the R square and so on, because the model is not significant. So what you're going to do is, one of the solution that I can provide you is the model is not significant. You need to look back into your parameter range. So you need to look back into the parameter range and do back the preliminary experiment. So the range might be too big or too small. So that's why I said that the range of your parameter is important. If you do it without a very critical analysis on the literature review, so what happens is, when you do the experiment, the model will not be significant. For example, the reaction will undergo at temperature 80 to 120. Then you do the experiment at temperature 40. So reaction will not happen. So that's why it's critical to know the level of your parameter. Second problem is the lack of fit is significant. A lot of people will do that. The model is very good, already significant. And you have a model term is also significant. But your lack of fit is significant. How to do? So no need to repeat all the experiments. So just repeat the experiment at the repeated value. You know that earlier we said that we have 3 repeated value. So see back the 3 repeated value. See the value of your surface response. So what is the difference? So why they suggested you the same parameter? So why the value is different? For example, you got around 100, 150 to 100. Why the range is too big? Normally, if they suggested you at certain temperature and certain time, if the time and temperature is fixed, the value should not vary that much. Maybe plus minus 5 to 10. So that's important to do the lag of fit. The solution is repeat the experiment at center point. The value should not vary too much. So what happens if the R square is not even close to 1? In this case, your R square is 0.6, 0.4, 0.2. Suppose we need to be close to 1. In different fields, they set the R square at different manner. In social science, it's around 0.6 above is acceptable. In science, pure science, normally in my lab, I put you need to get 0.8 above, but 0.7 is acceptable. So what you need to do, look at back your normal probability plot. You see here, you can repeat some of the data. This is almost showing the heavy hit because some of the only two data like here, and you have very far away data here. You can repeat this one, the red color one, and also the below here. You can repeat the experiment. So you just repeat these two experiments to see what happened, what is the impact toward your R square. So when I repeat the experiment that deviate from the predicted value, so I can get the R square close to 1. So don't take much hassle. Don't repeat all. So you need to work smart. You need to repeat the one that deviates from the predicted value, not repeating all. So means that repeating all might not get you the desired outcomes. Okay, next, the normal plot show heavy head or heavy tail. This is heavy head, you see? You only have one data at your coded -15. However, all the data at the positive side means that if you have heavy head, what means that your range is not accurate. So that means that your range is too big. You should not cover certain area of the range. So what happened is to get back into your parameter range. So you need to do some preliminary experiment to determine the range accurately, whether it is too big or too small. And last but not least, the data beyond the outlier. So how to know that? There is one of graph. They show you the standardized residual versus predicted. Okay, the red color is your outlier. And if data flow beyond the outlier, you need to repeat that certain data. So just repeat that data that I see the outlier. Okay, I think that's all. Thank you very much.
Okay. Thank you, Professor Mohammad.
Yes.
Thank you for your lecture. This is what is wonderful in science, no? When you were giving us your lecture, you remind me a few months ago when we were optimizing our SPR sensors with Taguchi method. And you mentioned something similar. For example, when you talk about factors and levels to optimize the response. And I suppose that when you talk about an ANOVA analysis, when you refer to F parameter, if F is higher, there are variability between groups. And if F is small, there is the same variation between groups and within groups, right?
Yeah.
It's the same, right?
Yeah, correct.
Okay. Let me share you a few questions in our platform.
Okay.
And a student is asking me, how do you know that the expected results from DOE are correct or reasonable?
Pardon? How do we know?
Yeah. how do you know that the expected results from DOE are correct or reasonable?
Response, you mean that the response data shown by DOE or what? We know if the response from DOE, you want to know that whether it's good or not. First, see the model first. The model should be significant, followed by the lack of fit should be not significant. Then the R square need to close to 1. If you have a bias and you don't believe the model, you said that you don't want the R square to close to 1. So it's mathematically wrong. The R square should close to 1 instead the model to be fitted. So in order to see whether you want to believe the model is good enough or not good enough, depending on the set of parameters, is very important. So look at back your range of parameter, range of factor. If you do the experiment and never get a very good result with the R square is haywire, not close to 1, then it depends on how you set your parameter. So in the end, my question, to answer your question, look at back in your parameter range. It's very important whether to determine is good or not.
Okay, I think this is enough. And the second question is similar. Maybe this is answered. How to know that the chosen model of DOE is the correct one for our experiment? Is similar.
Okay. During the presentation, I already show you how to know the correct model is good or not. Let's say you are anticipating a curvature, means that when you increase the parameter, it's slightly increased, at the middle point is the highest, and when you further increase the parameter, your response drops. So means that you see a curvature trend. So a quadratic and cubic is very good in that trend. If your data just goes straight line, when you increase how many times you increase, it just goes straight, then you might anticipating a linear or two-factor integer. And don't worry, if you don't know how to expect, the model will highlight for you which one is better based on your actual experiment. Sometimes what we're predicting and what we do the experiment might be a little bit different because a lot of factors. So actually the design have interface that will also show you which model will be expecting based on your actual data.
Okay. And Muhammad is asking something that I was asking too. How we get to know that which statistical model we have to use for optimization? Taguchi, RSM, full factorial, how to decide it?
Okay, in terms of decide, I think depend on your response. If you have experience on Taguchi, you can go to Taguchi. In my expertise in the RSM is more on you discussing the variable and towards the surface response. How you change the variable and surface response also change. If you already have knowledge in this, also you can use this. Depend on actually someone's ability to use the optimization. In the end, all the optimization tool is almost the same. We want to get the optimized material and optimized procedure. Depends on the resources, the knowledge, and also the expertise. You can choose either one. If you also have the knowledge in machine learning, you can also design yourself, coding yourself, the optimization tool. This RSM is for those who don't know the coding, but you want the template for optimization. If you already have Taguchi, you can use Taguchi. It's no big problem for me.
Okay. Another participant, Kabiraja. Usually the response is considered higher is better in the CCD or BBD. What if our response is lower is better?
Okay, for central composite design and box beacon, in terms of response means that this dual standard error, yeah, you might experience a little bit different because you know that the difference between CCD and BBD, for central composite designs, your factor will go to a critical value. But for box beacon, the data or the designs only centered around the box. So box beacon might be a little bit easy for the newbie. And for central composite designs, actually it depends on the experiment. If the experiment can cope to the critical parameter at very high temperature, very low temperature, you can go to CCD. The difference, I think, is not that much for CCD and BPD.
Okay, another question. What the importance of different outputs from DOE?
Different outputs means that the different surface response.
Different outputs.
Okay. Okay. For example, if you have different output or different response, each response will have their own ANOVA. And in the end, during validation test, they need to set the goals for that output. For example, you have specific capacitance, you have the output of limit of detection. You need to put the constraint on the output, whether you want to be maximized or minimized. In my personal experience, if you have multiple outputs, it's a little bit difficult because in the end, you want to correlate between different outputs into one outcome. Let me share you one example because one of my application is dual application supercapacitor. I'm doing electrochromic supercapacitor because electrochromic supercapacitor, even it share the same reaction mechanism, which is both should have redox. However, when you have a very high specific capacitance, your electrode color is very opaque. So transmitter will have a very bad delta, means that less light will pass through your electrode. So when you want to have high specific capacitance, the transmitter will also affect it. That's why you want to have a middle point. When you have multiple outputs, you need to declare which one you want to prioritize. So that's my opinion. So a little bit tricky on different outputs in the RSM, but it's doable.
Okay. Well, someone that I think it was expected. What about AI models for process optimization? Which is more reliable, the statistical model or AI model?
Back to answer the question, the same. If you're expert in AI, go for AI. So no limits in research. We also now in the field or in the technology around the AI, you got to coding, they can do coding for you, depends. It's also acceptable. I also see a lot of paper that combine the machine learning into the research paper, RSM into the research paper, all have their own benefits. So I think depend on your specialty. If you already expert in the AI, so why not? It's also the same optimization tool. In terms of AI, you have a lot of freedoms. You can put anything you like in terms of p-value, in terms of the limits, and so on. But for RSM, it's just like a template for you. You put the data and you get the result. It's like that.
Well, there are many questions. I'm gonna mention one more. Anyway, the organizer is telling me that Q&A question and answer session is open for all that drop their question. Only one final. Can we use the same software to optimize the condition for hydrogen generation and carbon dioxide reduction application?
But then the first one?
Can we use the same software to optimize the condition for hydrogen generation and carbon dioxide reduction applications?
Yes. To answer your question, yes. It depends on the application. If your application is HER, carbon dioxide utilization is also yes. You need to know your response is what. Like carbon dioxide is what? Percentage of carbon dioxide, HER, you want to study what? Overpotential and so on. Everything is possible. You just need to know your response, what is your desire. Like HER, OER is about the overpotential. The lower the overpotential is better. So you put your surface response as overpotential. So it's possible. It doesn't limit to the energy storage. You can carbon dioxide capture is also can.